The way that you read these and determine the actual chemical formula really isn't that bad. The main rule is to understand is this. Every end of a line or bend in a line is a carbon. So everywhere where you just see like a vertex, these are all carbon atoms, or the intersection of a line. Everywhere there's a bend in a line, that's a carbon. And everywhere that there's a line that just kind of ends, that's also carbon. You can't hide anything but carbon, so this molecule has only carbon and hydrogen atoms, and they're all hidden. But we just found all the basically pointy parts in the ends. That is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is C9. Okay, we're off to a good start. How many hydrogen atoms are there? The thing that you've got to understand about carbon is that carbon can have up to 4 bonds. And those bonds can come in a variety of types. So let's draw it. Carbon can have 4 single bonds. Carbon can have a single bond, a double bond, and another single bond. Carbon can have 2 double bonds. Carbon can have a triple bond and a single bond. That's all the possible ways that carbon can have 4 lines touching it. But no matter what, it's got to have those 4 bonds. If you do not see anything on that carbon, you've got to assume that there are hydrogens there. Here's what I mean by that. If we take a look at this top carbon here, this carbon has 3 lines on it, which means it has one more available hidden line, or one more available hidden bond. So that hidden bond is where a hydrogen is. I'm going to draw in where the hydrogen would go. Now notice how that same structure is found over here, and here, and here, and here. Those all have hidden hydrogens because they're a carbon that has 3 of the 4 possible lines on it. This carbon here, notice how it already has its 4 lines. It's full up. It has 2, 1, and 1. It has a double bond, a single bond, and a single bond touching it, so there's no more room for a hydrogen to even exist there, which means that there's no hidden hydrogen there. If you look at this carbon, that particular carbon has 2 lines, which means it has 2 more available lines, which is where the hydrogens are hidden, to save space, of course. And then we have an available hydrogen spot here, because that carbon has 2 plus 1, so it's 3. That means that one of them is hidden, which I just drew in. And then the carbon on the very right has 2 explicit bonds. I'm going to draw in those 2 hidden hydrogen connections. If we count up all our hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is C9H10. That's how you read that formula. Let's do the next one. Count up all of our carbons. We have an intersection, an intersection, an intersection, an intersection, and an intersection. Remember, you can't hide anything but carbons and hydrogen. So this chlorine here has to be explicitly known. This is not a carbon, that is a chlorine atom. The chlorine atom is at the end of that bond. So right now we have 1, 2, 3, 4, 5 carbon atoms. How many hydrogen atoms do you see? Trick question. The answer is none. However, there are hidden hydrogens, and using that same rule, we can just count how many lines are there touching that carbon and how many ones are available after that. So let's start over here. We see that there are explicitly 2 lines or 2 bonds for that carbon, so which means that there are 2 available spots for hydrogen to exist. Same thing is true here. But this carbon right here is a different story. It has 3 lines touching it, which means there's only available spot for 1 hydrogen. Same is true for this one. What about that final carbon? There are 3 lines or 3 bonds, and it can have a maximum of 4. So that means that one of them is hidden, and that is a hidden hydrogen. Now we can count them up. 1, 2, 3, 4, 5, 6, 7. This is C5H7, and of course, don't forget the chlorine. Lastly, we have another molecule with carbons and hydrogens that are hidden. Now this one, because you don't see any Cl's or N's or any other letters, the only atoms here are carbon and hydrogen atoms, just like with the first one. So let's find all of our carbons. We have 1, 2, 3, 4, 5, 6, and 7. So we have C7 as the start of our chemical formula. There are some hidden hydrogens, of course. This first carbon has 1 explicit bond, which means that 3 are there. 3 hydrogens are there. I'm not going to draw the H's because we know the orange means hydrogen here. And then this carbon at the bottom has 1 explicit bond, so we have 3 hidden hydrogens there. And the carbon in the center of that 3-way intersection has 3 explicit bonds, so only 1 hydrogen can be hiding out over there. We have 2 hidden hydrogens off of that carbon. And look carefully here. We got a carbon here, and it has a single bond on one side and a triple bond on the other side. 1 plus 3 is 4. That means that there's no hidden hydrogens because there's no more available spots. And the same is true for the other carbon that has a triple bond. because there's a single bond on the other side of that. So both of these carbons have no hydrogens on them. The only remaining hydrogen atoms that are hidden are the one on the very end. Because there's one explicit bond on that carbon, that means there are 3 hidden hydrogens. Count up your dashes: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is H12. And that's it. That's the chemical formula for these. If you remove all the blues and all the orange and stuff, you'll get back down to the skeletal structure, which is the one that has hidden hydrogens and hidden carbons. But you can't hide anything else. That helps you understand how these structures work.